Okay, everybody, welcome. Thank you all for turning out for the Math Club. It is my pleasure to introduce Professor Lance Ouyang, who is going to tell us all about convexity. Lance?
All right, thanks, Jim, for the introduction. It's great to see you all for this talk. So today I'm going to introduce something really straightforward. It's convexity, and it's convexity of a two-dimensional set. So first of all, what is convexity? Convexity is really straightforward to describe. So basically, you have any set. You just consider 2 points on the set. So here I've already chosen 2 points, x and y. And if you connect the line segment between those 2 lines, and the line segment stays in the set, then we say that the set is convex. So here, obviously, we have an example of a convex set. This is just something I draw randomly. And you can easily draw a non-convex set as well. So the set over here is non-convex. The reason is because if you pick an x over here and then a y over here, draw the line segment, some part of the line segment would not belong to the set. And therefore, well, for example, the blue one I illustrate over here, this blue point over here is by no means inside my set. My set is over here. Okay, so this is the non-convex set. So this is really straightforward. There are many examples of convex set, and we can give some straightforward examples. For example, a half space. So when I say a half space, what I mean is that, well, consider two-dimensional. As I said, our discussion today is just a two-dimensional set. So consider a two-dimensional set. You draw a line, and whatever that's above the line or whatever that's below the line is a half plane in this case. And in high dimensional, it's half plane. Now, draw any 2 points. The line segment is going to stay above or below the line. So, so this half space or half plane is obviously a convex set. We have another example. Two-dimensional again. So whatever that's within a circle, this is what we call a disk, is going to be a convex set. All right. Again, straightforward to see how it works. There is a difference, we always say, between disks and circles. We need to pay attention because when we say disk, it is whatever that's inside the circle, including the circle itself. And anytime we say a circle, it's just going to be the circle itself as the set we're talking about. And in this case, it's not going to be convex. The reason is because I choose any 2 points in the circle, as long as the 2 points are distinct, connect a line segment, well, then other than the 2 points, any other points on the line segment is not going to be on the circle. And therefore, circle is an example of a non-convex set, just for this obvious reason. If we go for one more example of a convex set, we can consider the region within a ellipse. So over here, again, I'm not talking about the ellipse itself. I'm talking about everything that's inside, including the ellipse. And again, picking any 2 points is easy to say. It's easy to see that the line segments are lines within. So this is convexity. Here, well, looking at a circle and the ellipse, there is a pretty straightforward observation that in order to get an ellipse, all I need is to start from a disk or from a circle and then stretch it, all right, shift it a little bit or rotate it. Over here, this example of an ellipse I give is not rotated, but it's shifted and it's stretched both horizontally and vertically. So this is what we know as a linear map between the sets. The reason is because if we look at the exact description of the disk, the exact description of the disk is over here, x1 squared plus x2 squared less or equal to 1. And looking at the ellipse, it's like this. So what happens is that, well, I intentionally use y1 and y2 and x1 and x2 for ellipse and the disks over here. The thing is that I can easily do a linear transformation. Then I go from a circle to the region within ellipse. And the inverse of this linear map is also true. I can easily go from ellipse to a disk. So I can always do this kind of linear map between those two sets to get to go back and forth between disks and whatever that's within the ellipse. Okay, I'm trying to erase this one and fail, but that's okay. Now, this is another property that's very important for convex sets. I'm not going to prove it over here, but it's something that we can prove by the definition of convexity exactly. So linear maps of convex sets are still going to be convex sets. If you want it in mathematical terms, here they are. Okay, so what we're saying is that linear maps of convex sets are going to be convex itself. But what about nonlinear maps? Well, we can easily find a contradiction. The nonlinear map over here, I'm going to consider is going to be the following. It's again straightforward. X is over here. So this is my X. X is the interval between 0 and 1. And I do a map. The map is going to be the following. It's going to be a map from one-dimensional to two-dimensional. And in two-dimensional, what happens is that the first coordinates of this two-dimensional set is going to be exactly the x I have previously in the interval. And then the second coordinate is going to be x squared. So what's this? This is part of the parabola. Okay, this is the graph of part of the parabola between 0 and 1. And obviously, this graph is not a big convex. It's exactly the same arguments that we had previously when we were looking at circles as well. The reason is because I pick any 2 points and draw a line segment. Then other than those 2 points, anything in between in the line segment is not going to stay on the parabola. And therefore, there is no way this is going to be convex. So we know that linear maps of convex sets are convex. Nonlinear maps of convex sets, we cannot guarantee. Okay, so that's the introduction of convexity. It's fundamental. And if you think about it, we can easily imagine and illustrate what kind of convexity is, especially if it's 2D, okay, if it's two-dimensional. Now, here comes the theorem that I would like to introduce today. So the theorem is proved by Brickman in 1961. It is stated in the following way. So suppose dimension n is greater or equal to 3, and I have 2 symmetric matrices of n by n. I denote them by A1 and A2. And then I consider the following set. The set is a two-dimensional set. The first coordinates of points in this set is going to look like x transpose A1x. And the second is going to look like x transpose A2 times x. And the x ranges from any x on the n-dimensional sphere. So that is to say the sum of the sum of squares of all the coordinates of x should be equal to 1. This is it, as simple as this. Well, it can be as simple as a two-dimensional set, and at the same time, it is something that's originated from the n-dimensional sphere. So it can be a little bit sophisticated if we think about the structure of x. X can be high-dimensional. It can be, a million dimension. That's still going to be fine. Now, here I introduced this kind of notation of x transpose matrix times x. This is just the linear algebra kind of notation. If you are familiar with algebra, an alternative way of doing it is just treating those as polynomials. So essentially what happens over here, this is just going to be a homogeneous polynomial of n variables, and that's it. So Brickman's theorem is going to be in this statement. Now, suppose that we, let's try to absorb what happens, and let's try to digest what this theorem is about. This theorem is basically saying that if I look at all the points, on the sphere, and I consider a map from the sphere to this two-dimensional set, and then the map is defined by quadratic forms, quadratic maps, then this two-dimensional set I obtain at the end is going to be a convex set, and that's it. Let's take a look at very simple examples just to understand what this theorem is about. Okay, what this theorem is about is, well, let's do a very simple example. The first case, suppose that the matrices A1 and A2 are identity matrix and negative identity matrix. So the X transpose times A times X. Well, if you wanted to do the multiplication, you're familiar with the linear algebra, you can do this. If you don't want to, well, it's obviously a x1 squared plus x2 squared plus x3 squared, this kind of quadratic homogeneous polynomial. So for now, if you don't, if you don't like those kind of notations, you can focus on the polynomial notations. I give all those polynomial notations for the examples. All right, so the first case is straightforward. This is actually a pretty simple example. So it's the set of points that look like this, that's mapped from the three-dimensional sphere. Well, three-dimensional sphere, sum of squares of any of the coordinates of any point on the sphere has to sum to 1. And therefore, this set I'm talking about is just 1 point. Okay, it's a singular point, and therefore it has to be convex. The reason is because you pick any 2 points. Well, there is only one. Do the line segments connecting those 2 points, you get this point itself. And therefore, this singular point set has to be convex. So we're done. Okay, let's do an example that's a little bit sophisticated. In this case, what happens is that we're going to talk about a map from 4-dimensional sphere to 2-dimension. Okay, the description of the quadratic polynomials are like this. So the first coordinate is going to be x1 squared plus x2 squared. Second coordinate is going to be x3 squared minus x4 squared. So how does this look like? There is actually a relatively simple way to write down the set in an equivalent way. The reason is because if you take a look at my description of the set, I only have squares. I have x1 squared, x2 squared, x3 squared, x4 squared. Okay, I only have those descriptions. Therefore, I can let y1 to be x1 squared, y2 to be x2 squared, y3 to be x3 squared, and x4 squared, well, I don't need anything because no, x4 squared is 1 minus the sum of y1, y2, y3. So what does this set look like? Well, after I do this transformation, I end up with a description using y1, y2, and y3 only, because x4 squared can be described by y1, y2, and y3. And y1, y2, and y3, because they are squares, they have to be greater or equal to 0. And originally, this sum is equal to 1, but because x4 is not considered anymore, so the sum of y1, y2, y3 has to be less or equal to 1. And then I can also transform this sum, this difference to this form. Okay, now let's start taking a look at what this set will look like. The easy stuff, the easiest thing we can do at this time is that we realize that this is a linear map of a set in a 3-dimensional space. So we can actually draw the set and just illustrate the set itself. Okay, so if we draw the set, they look like this. Okay, I draw the plane y1 plus y2 plus y3 equal to 1 in 3D. That's over here. And then I look at the first octant, whatever that's below this plane. So it's this polyhedron. Okay, this is called a extended simplex. All right, so it is a polyhedron. It is convex. It's straightforward if we look at the shape of it. And then, as I said, linear maps of convex sets are still going to be convex set, and then we're done. Okay. Now, if you don't believe me, I can draw this set for you, and I'm actually going to draw some more sets afterwards, including this one. But let's hold on it for now. The next set I'm going to give is going to be a little bit sophisticated to interpret. Okay. The next set I'm drawing is the set defined by those 2 symmetric matrices in 3-dimensional. So the polynomial kind of distribution you look at is something like this. So it's not really straightforward to see the shape of the set like this, okay? Because of this x2, x3, and I can no longer make that easy, transformation of introducing y1, y2, and y3. But luckily, there are still ways to illustrate the set. So let me change my screen and let me try to share the other screen for us to see the images. Okay, so we have a code that's available to draw the set, and let me see. Yeah, Harrison Eggers is over here. It's great to have you here, Harrison, because this is actually the code that Harrison developed during the homework in the 8100 class, just for illustrating this set. So let's run this code, and I'm going to show you what everything look like. So let's see. The first one, let me actually enlarge this one so that we can see. Okay, so this is the first set I talked about previously. That was a linear map from the extended simplex. Okay, it was a linear map from a convex set. All right, so this is a triangle in 2D, and whatever that's within the triangle stays in the set. So this is the set that I was talking about, by changing our variables y1, y2, y3 as x1 squared, x2 squared, x3 squared. This is the set that we can observe. So this is something that we can illustrate. For the next set that I mentioned previously, that involves like x2, x3 in the polynomial. So it's not necessarily easy to see how to reformulate and describe the set, but I can actually draw it by this code. So it's pretty much like whatever that's within this egg shape. Okay, so this is the set I introduced as one other example that's within that includes x2 times x3 terms in the polynomial. Now next, I'm going to generate some more sets, and this time the set would be generated by looking at the x from dimension, I believe 7. Okay, so I can randomly generate many sets of those many of those two-dimensional sets by randomly generate symmetric matrices A1 and A2, and then look at what the shape of it. So here, let's show some more. So we have this. This is one example of the random shape of this set. It looks like this, whatever that's within. So this illustration is only the boundary of this convex set. Again, it's easy to see that this is convex. And one more, totally different kind of shape, but it's randomly generated. And whatever that's within, this is also a convex set. Please be aware that the boundary of this set, some part of it looks even like line segments. But again, this is still a convex set. And I have another random generation. This is another set that look like this, and I can keep going. Then there is this. I forgot to make sure that it maximizes all the time. But yeah, then there is this shape. Then there is this shape. There is this shape. You can see all kinds of shapes that looks totally different from each other, and those are all randomly generated. I randomly generate the symmetric matrices, and then I draw the graph. The code is really simple. If you take a look at it, so it takes less than 10 lines, and we're done. This is something that's thanks to Harrison's homework development. All right. Now we have the illustration, and you can see that all the shapes we generate over here, the two-dimensional sets are all convex. So what's behind this this phenomenon? Why do we have this kind of convexity? Well, if you think about it, it's kind of amazing that we would have this convexity. And well, what happens is that if you think about what happens, all right? So this is a convexity result that's in some sense hidden in somewhere. The reason why we say it's to be a hidden convexity result is because of the following. As I said, linear maps of convex sets are convex. We can prove that. Nonlinear maps of convex sets are not necessarily convex. Here, what's intriguing is that we're talking about image of a non-convex set, because we're talking about sphere. Okay, n-dimensional sphere. Remember, circles, spheres, they're not convex. And it's under a nonlinear map because we're talking about quadratic map. So this is nonlinear. And somehow the set we end up with turns out to be a convex set. Okay, so this is why we call it a hidden convexity result. Okay, so at this point, it seems that there is no obvious reason why this is true. But the goal of my talk today is that I'm going to try to introduce a elementary proof of this theorem that was done by Ouyang in 1973. So before I move forward, I want to let you know that in this statement, I need to make an assumption that n is greater or equal to 3. Okay, so this sphere has to be at least dimension 3. I'm talking about a map of a dimension n and greater or equal to 3. Okay, the counter example of dimension 2 is the following. It's also an example that is interesting to observe. Okay, two-dimensional case. So the two sphere is going to be a circle. And those are the polynomials that I'm introducing. So if I take a look at this set turns out to be the circle. This set itself is actually the circle. And therefore, as I said, circles are not convex. The easiest way to see this is just taking the square of the first coordinate and the square of the second coordinate. So take the squares, sum together. We're going to realize that we get the square of sum of squares. Okay, so it looks like this. And because x1 plus s squared plus x2 squared has to be 1, x is in the circle. So we end up with y1 and y2 that's on the circle as well. So we're done. So n equal to 2 case, there is counter example. We have to focus on n greater or equal to 3. All right, so let's go over a really interesting proof of this one. The proof is the following. So we're gonna need a result to prove the theorem. Okay, this result is stated in the following way. All right, so what happens is that Brickman theorem says that we're gonna have two symmetric matrices A1 and A2. Here I'm gonna introduce two symmetric matrices that's not A1 and A2 but B1 and B2. So those are slightly different, two symmetric matrices. And I'm gonna have a requirement of those two symmetric matrices B1 and B2. I want to make sure that for any non-zero vector in Rn, this U transpose B1U and U transpose B2U, so basically the image of any non-zero n-dimensional vector under the map described by symmetric matrices B1 and B2 is always going to be non-zero. And then if this is the case, then the result says that if we consider a map from n-dimensional sphere to a two-dimensional circle that's defined in this way, this is what the map looks like. This map is a map from n-dimensional sphere to two-dimensional circle. And the result is that the image of this map is going to be a closed circular arc, and it's going to be having an arc length. This is of arc length less or equal to less than pi. It's not going to be less or equal. It's strictly less than pi. So if this looks sophisticated, I'm going to give you a illustration. Hopefully, the illustration is going to make it much more clearer. So the illustration is going to be the following. So for any B1 and B2 that satisfies the assumption I mentioned, there exists this map. Okay, the assumption makes sure that the denominator is non-zero. So how does it work? Well, I look at a high dimensional sphere. For example, with this illustration, I have a dimension 3 sphere. Then for the map, the image of all the points in this n-dimensional sphere is going to be a closed circular arc in the circle. And this arc cannot have length greater or equal to pi. That's it. Okay, so this is the result. And if this result is true, then Brickman's theorem has already been proved. The reason is going to be the following. So here, let me pause for a few seconds. Let's try to digest what we're doing. We're trying to prove the convexity of a set. The set is a map from n-dimensional sphere to 2 dimension based on 2 matrices A1 and A2 that are symmetric. Now, the proposition we rely on to finish the proof basically says that for any 2 symmetric matrices, B1 and B2, that satisfies a certain property, I can introduce a nonlinear map that maps from n-dimensional sphere to 2-dimensional circle. Okay, and then this image of the map has to be a circular arc whose length is less than pi. Okay, so let's assume that this proposition is true, and let's see how it helps with our proof of Brickman's theorem. Okay, I give a remark over here that if you're familiar with topology, I believe, which I am not, I think this is related to the fundamentals of algebraic topology. If you're familiar with this, this is actually a very important property of maps from high-dimensional sphere to circles. There is a topological explanation that can be derived that's similar to this result by looking at Calabi's statements in 1963. So basically, spheres, the maps from spheres to circles are unique in the sense that they have very special topological property. And this is a special topological property that you can observe. All right. So now with this proposition over there, we are ready to start the proof. We're going to prove the theorem by contradiction. The proof is done in the following way. So I choose 2 points on my set. This is just by definition of convexity. I'm not doing anything. I'm basically claiming that if I have any 2 points, okay, on the set I'm interested at in Brickman's theorem, then the line segment connecting the 2 points would always remain in the set. And I suppose that this is not true, and I do it by contradiction. If I do it by contradiction, then that means that there exists a point on the line segment. So basically there are 2 points. There is 1 point over here. There is 1 point over here. I'm doing it by contradiction. We're going to say that there is this point that does not belong to the set. Okay, suppose that the set is not convex. So I should be able to have this kind of contradiction. I should be able to have this kind of counter examples, and then I'm going to prove that this will not hold. Okay, so suppose that suppose that this is suppose that the counter example exists. Suppose that the set is non-convex. Please be aware that to define points in the set, I have to rely on x and y in n-dimensional sphere. Okay, and then here I have a set. I have a point. Sorry, here I have a point on the line segment that do not belong to my set. What does this mean? Well, our set, the Brickman theorem, the set is defined, always defined in this way. Just remember, it always look like this. All right, so where the x is in the n-dimensional sphere. So this is the set we're talking about. Then therefore, if we say that there is a counterexample, what we are saying, what we are really saying is that this point as a counterexample cannot be represented by this notation. Okay, so I am not going to be able to find a point on the unit sphere. In other words, I am not going to be able to find a non-zero vector and then divide by its magnitude to have a vector in the n-dimensional sphere that represents the counterexample. So this is again nothing. This is just definition of convexity of my set. So we're going to assume that this does not hold. If this does not hold, what's going to happen? Well, so if this does not hold, what happens is that I'm going to start introducing a matrix B1 and a matrix B2, just designed specifically to this counterexample I'm having. So what happens is that B1 is going to be defined as the matrix I'm considering in the problem minus a value times identity matrix. B2 is going to be the matrix A2 defined in the definition of the set minus a constant times identity. Okay, so this statement, what does this statement mean? So this statement is saying that there exists a counterexample. So what's going to be the fact of this counterexample? The fact of this counterexample is basically the following. For any non-zero u, this cannot be zero. The reason is because if I try to compute u transpose B1 times u is going to be equal to u transpose A1u minus this constant over here times the magnitude of u squared. And if this is equal to 0, that means this equality is true. Okay, and then the second coordinate equal to 0 means that this equality is true. And as I said, our assumption is that those equalities could not both be true because I'm not assuming that my set is convex. Okay, now somehow I introduce a matrix B1 and B2 that's based on the description of my set A1 and A2. Okay, so this B1 and B2 satisfies the assumption I had previously for the proposition. Now, with some computation, I can actually compute X transpose B1X, X transpose B2X, Y transpose B1Y, Y transpose B2Y, and realize this interesting relationship. So basically, this point and this point are going to be scalar multiples of each other. But at the same time, this lambda is between 0 and 1. Okay, we can skip the technical details if needed. But the point is that if the set is non-convex, then what I am able to do is that I am able to introduce a matrix B1 and a matrix B2 and find out suddenly two vectors that are of opposite direction to each other. Okay, so this is what this statement is. So the illustration is basically saying that if Brickman's theorem were false, then I am able to find the two vectors that are opposite direction of each other. So, well, if I have two vectors that are of opposite direction to each other, I can divide the vectors by their magnitude to push them in the unit circle, in the circle we're talking about. So we're just going to divide both sides by the magnitude of the two-dimensional vector, divided by magnitude. So what's happening is that pushing them in the circle, I'm going to have two vectors that are on totally opposite sides of this circle. So what does this mean? Well, what this means is that if I go back to the previous proposition, okay, what did I say in the previous proposition was that for B1 and B2, satisfying our assumptions, there is this map F. F is described like this. There is this map from n-dimensional sphere to a circle, and the image of this map F has to be a circular arc of arc length less than pi. But here, if Brickman's theorem were false, then I have a contradiction. The reason is because I pick X as a point on the n sphere, Y as a point on the n sphere, and by the counter example, I assumed in Brickman's theorem, the image of X in the circle and the image of y in the circle. So this point and this point, they're going to be opposites of each other on the circle. Well, in this case, what does that mean? Well, that means the image of f is not going to be a closed circular arc of arc length less than pi. It has to have a length at least equal to pi or greater or equal to pi. So we have a contradiction, and then we're done. Okay, so oops. So by this contradiction, we are done with the proof of Brickman's theorem. So if you think about the proof over here, up until this stage, I'm not doing anything fancy, essentially, because what am I doing over here? I am only considering a contradiction. I'm supposing that the set I'm looking at, this set, I'm assuming that this set is non-convex. And if this set is non-convex, then, well, there has to be a line segment connecting 2 points such that 1 point on the line segment do not belong to the set. And then what I'm saying is that, well, if there exists such point that do not belong to the set, then that means I am able to somehow generate 2 vectors of opposite directions, and therefore pushing them to points over the circle. I can find a counterexample of the previous proposition. So basically, for the map that I was interested at previously, in proposition number 2, the map of n-dimensional sphere is not going to end up as a closed circular arc of arc length less than pi. Okay, so any questions at this point? Again, I have not proved that proposition that this arc length is less than pi, but any question at this point? So if there is no question, we're just going to have to continue and finish the proof. Again, just if we pause at this stage, we're not doing anything extremely technical. All we are doing is just by algebra computation and showing that if there is a counterexample, I can actually compute things somehow, and I figured out two-dimensional vectors that are of opposite direction. Okay, so at this stage, there is nothing that's technical. Now, next step, I need to prove that proposition. So basically, I need to prove this claim that for the specific map I'm talking about, there are maps from the sphere to two-dimensional circle. The image would never be an arc length. The image would never have arc length greater or equal to pi. Okay, so we still need to continue with the proof. This proof is still done by contradiction, and it's exactly the same kind of contradiction that we used previously. So the proof is going to be the following. So the proof is what we're trying to prove this. The first is we need to show that this is the closed circular arc. Okay, the image has to be proved to be a closed circular arc. I'm going to skip this part. I think this is just a topological facts that we just need to use the property that the function we define is continuous, and then n sphere is connected and compact to show that this circular arc is closed, and it's a circular arc. The next part is the real part that's technical in this proof. But I'm just going to claim that if you know linear algebra of dimension 3, and if you know how to solve quadratic equation systems with 2 variables and 2 equations, then you are able to finish this proof. So the thing over here is that we are going to make exactly the same kind of assumption that try to derive a contradiction. So we're going to assume that that circular arc is not going to be arc length less than pi. Instead, we're just going to assume that on this circular arc, okay, there are going to be 2 points that are opposite to each other. Okay, so suppose I am able to get a B naught, A naught, B naught, 2-dimensional points on this circle, and a negative A naught, negative B naught on this circle. So suppose this is the case. So suppose this is the case, what happens? Now, I assumed that the map, I assumed the look of the map. Okay, the look of the map is basically a map from n-dimensional sphere to 2-dimensional circle. So, so for those 2 points belonging to the image, I should be able to find 2 n-dimensional vectors over the n-dimensional sphere, u and v, such that the images of u and v are going to be the 2 points on the circle. Okay, so take a look at this equation. So I'm not doing anything. I'm basically saying that suppose there are 2 points on the circle that are opposite to each other, and suppose that they are generated by u and v from the map F. Okay, so suppose this is the case. Suppose this is the case. What's going to happen is that there's no way that u and v are going to be scalar multiples of each other, because if u and v are scalar multiples of each other, say let's say u is equal to say mu times v. Okay, so then here I can plug in mu times v, plug in mu times v. So this is going to be so left hand side I am able to connect this point and this point by saying that a naught b naught is equal to negative u squared, mu squared times a naught b naught. Well, this will not be the case. The reason because they are opposite directions, and mu squared is always greater or equal to 0. Okay, so there is no way that that this negative direction vector are positive multipliers of each other. There's no way. So obviously u and v are not going to be scalar multipliers. Well, here comes the fact in linear algebra. If they are not scalar multiples of each other, then they're going to be linearly independent. So u and v are linearly independent. Again, u and v, remember that they are n-dimensional. They are non-zero. They are linearly independent. Okay, here comes a fact in linear algebra. N is greater or equal to 3. Okay, so in this 3-dimensional space, if you have 2 linearly independent vectors, you can always do the so-called basis extension to find one more basis vector, such that the 3 u, v, and w are linearly independent. Okay, so basically, this is what happens when dimension is greater or equal to 3. You can always do this. Okay, so what's the definition of a linear independence of 3 vectors? U, v, w are n-dimensional vectors. Linear independence means that there is no way that I am able to find the 3 coefficients not all equal to 0, such that the linear combination of the 3 vectors u, v, and w is going to be equal to 0. Okay, so this is what we know by linear independence. Linear independence is like this. Okay, so there is no way for me to find the non-zero coefficients such that linear combination is equal to 0. The assumption I had for B1 and B2 in the proposition is that as long as my point is non-zero, then there is no way that the vector transpose B1 vector transpose B2 vector, the 2 quadratic forms are going to give me 0. Okay, so this is the assumption of the proposition that I had. The assumption is that there is no way that this is true. The reason is because there is no way that the coefficients are non-zero such that this is equal to 0. And the assumption is that this is equal to 0 unless this is equal to 0. And therefore, by the assumption of the proposition, here is the statement that we have. There does not exist coefficients x0, y0, z0, not all equal to 0, such that this holds. Okay, let's pause for a while to digest what it means over here. From linear algebra point of view, the meaning over here is that here I have a linear combination of n-dimensional vectors u, v, and w. It's linear combination with respect to coefficients x0, y0, and z0. And this is the vector to me. I'm doing vector transpose b1 times vector. Okay, and there is no way that both those two vector transpose b vector would be equal to 0. Well, there is an alternative way. If I only focus on x0, y0, and z0, if I treat x, y, z, those real numbers, real coefficients, as variables, and try to solve a system of equations. Well, here I have a system of equations. And this system of equations with respect to x, y, and z are actually quadratic systems. Well, it's just because I have them over here, and then I have b1, I have this. Okay, so I actually have quadratic equations over here. So what else do I know for those quadratic equations? I actually know a little bit about some coefficients of this quadratic equation. So let's actually do an expansion over here. So let's do an expansion over here. What's the expansion over here? If I actually, expand everything, then what happens is that I should have something like this. I should have an x squared times, well, let's actually do it step by step. I should have a xu transpose b1 xu. All right. And then I should also have a yv transpose b1 times yv plus a bunch of other terms, done similarly. And what's this? Well, this is equal to x squared times u transpose b1u plus y squared times v transpose b1v, and plus a bunch of other things in this quadratic polynomial. But the key is that if I look at u transpose b1u and v transpose b1v, well, the interesting thing is that I've made an assumption about what they are. I know u transpose b1u and v transpose b1v. Okay, so they should be a0 and a negative a0 over here. Well, if this is the case, then after I do this expansion, if I follow that assumption of equation 2, here I should have a a0 times x squared minus a a0 times y squared plus a bunch of other terms with different coefficients. But nonetheless, the coefficients in front of x squared and y squared should look like this. And therefore, the first equation, it has to have a term of a0 times x squared minus y squared. Rest of the terms, I can also factorize them, and then there have to be some certain coefficients, a1, a2, a3, a4 for those quadratic terms, but it has to look like something like this. Okay, so the quadratic system I have look like this. Okay, so I have the following quadratic system. This is the quadratic system with 3 variables and 2 equations. And my claim originally was that this will not be true. If this will not be true, what does that mean? If I expand everything, that means this equation, that means this equation system, this quadratic equation system with x, y, and z will have no solution. Oh, well, no non-trivial solution. There is trivial solution, if you set x, y, z all equal to 0, then you have a trivial solution. The question is, do I have any non-zero solution? Well, here you see we have quadratic equations with 3 variables, 2 equations. I promised that you only need to know how to solve quadratic equation system with 2 equations, 2 variables. Why? The reason is because, well, I can just consider 2 different cases. The first case, I'm going to set z equal to 0. I'm going to set z equal to 0, assuming that this is true. Setting z equal to 0, I should be able to transform this equation 4 to this format. And this is for any real coefficients, a0, a1, b0, b1. Well, this one obviously has at least one non-zero solution because, well, those two equations are actually, redundant. You can reduce them to one equation just because this equality is true. Okay, so in this case, nothing to solve, but there is definitely going to be non-zero solution. The second case, again, I'm going to set z equal to 1, and then I'm going to have an equation system that look like this under this assumption. All right, the way I'm going to solve this equation system is going to be the following. I notice that I can use Cramer's rule for solving linear equations with 2 variables and 2 equations. The way I do is going to be the following. Because the determinant is non-zero, I treat this as one variable, I treat this as one other variable, and treat the rest of them as constant. I solve for x squared minus y squared, I solve for xy. I should have something that look like this. Okay, as I said, those are treated as constants, but nonetheless, I can solve this. I can reduce this quadratic system to a quadratic system that look like this. Next thing we do is that we try to solve this quadratic system. And this is a little bit technical, but we are able to prove just by solving this quadratic system that there is at least one non-zero solution. Okay, so for either case, there is always non-zero solution. So what does that mean? Well, that means my claim over here. My claim over here is that there does not exist non-zero coefficients x0, y0, z0 that satisfies this. Well, I just proved by solving quadratic systems that there exists x0, y0, z0 that satisfies this, and therefore there is a contradiction. And well done. So that's the proof. I really like this proof myself. This is a little bit different from Brickman's original proof. The reason why I like this is if you try to go over what I've done over here, there is nothing fancy. There is nothing too technical. All the facts I'm using are definition of convex set. So definition of convex set, it's over here. Okay, definition of convex set. And if the set is non-convex, I am able to get 2 vectors of opposite direction, somehow end up with circles, and somehow violate this result. How do I prove this result? Well, to prove this result, I use nothing more than linear independence of 3 vectors and solving quadratic systems with 2 equations and 2 variables. Oh, well, there is, I admit, there is a little bit something that's hidden over here by proving that the map ends up with ends up as a closed circular arc. But this is some topology that can be figured out. All right, so here comes the conclusion. So now we know that Brickman's theorem is true. If we try to go back at what we've done, essentially this proof reveals that the maps from spheres to a circle is in some sense quite unique, and that property can be used while equipped with a proof by contradiction to prove the convexity results of Brickman. Again, this is a hidden convexity result because I cannot see at the very beginning why this is convex. This is the nonlinear map. This is the nonlinear map of a non-convex set. Okay, I only know that linear maps of convex sets are convex. And I even also know that nonlinear maps of convex set are not necessarily convex. But the interesting thing is that somehow this is true. So I'm done with the proof of Brickman's theorem. The interesting part, there are actually lots of follow-up things I would like to mention. First remark, there is, I think, in my mind, there should be a similar proof if we use topology. So when I say simpler, I mean reducing this proof of proposition 2 to a few lines. I think there might be a possibility. Unfortunately, I'm not an expert in topology. I know this is something that might be done using basic topology, but the thing is that this result there should be a proof using, I believe, algebraic topology. This should be similar to what Claby did in 1964 when he was proving a theorem that's really close to what we're doing over here. He was proving I think he was essentially proving a result that can be reduced to this theorem. All right. The next question, of course, if you take a look, we are using matrices all the time, A1 and A2. Is there any way to prove the theorem by using linear algebra? Well, Ouyang and Peng actually have a different proof, 1974. The alternative proof uses pretty much linear algebra, as long as you know matrices and the positive semi-definite matrices and the properties for two matrices to commute. We can finish the proof of Brickman's theorem if needed. Next, I suppose this is every mathematician would actually try to do after we see a proof by contradiction. We prove by contradiction that the set has to be convex. So the proof is that if the set is not convex, I should be able to derive a contradiction. But does there exist a constructive proof? What do I mean by constructive proof over here is the following. Suppose that I have 2 points on the set. Convex combinations of the 2 points, the line segments connecting the 2 points, can I prove that it stays in the set? That is to say, can I actually point out what kind of vector in the n-dimensional sphere is going to generate the line segment, the points on the line segment connecting the 2 points? So again, the illustration is over here. I have 1 point, I have one other point. I want to prove that for any point, on this line segment, it belongs to the set. It is not necessarily trivial. The reason is because the point, the description of the set relies on the image of n-dimensional sphere. So to show that a two-dimensional set, two-dimensional point belongs to this set, I need to show that there exists a point x in the n-dimensional sphere such that this two-dimensional description is equal to my two-dimensional point. So I need to show how this x can be computed. This is not necessarily trivial. Well, likely this can be done by using convex analysis. So this is actually a direct result through convex conic programming. One result I can refer to is Barbanok's book, 2001. Now, is there any alternate understanding? One thing I can say for sure is that this hidden convexity is actually not that kind of mystery. Barbanok actually pointed out in his book that the hidden convexity over here, while it looks really strange, nonlinear map of a non-convex set gives us a convex set. But well, it's actually a coincidence because you can prove that the set we're looking at is actually image of a convex set under a linear map. Well, this, well, if I have time, I would really like to go over this if possible, but I don't think it's going to be covered. We will be able to cover it in 1 hour or even 2 hours. There is fundamentals of convex conic programming that's over here that involves the cone of semi-definite matrices. That's the end of my talk. Thanks you all for coming. And I'm actually quite glad that I'm able to give this talk to tell you something that I'm enthusiastic about. This is something that really fancies me because of this convexity kind of thing that comes immediately from a nonlinear map of non-convex. All right, thank you. And let me give one more acknowledgement. I'm grateful that Harrison Eggers actually studied the illustration of this set, and I get even more interested about this problem after I saw Harrison's results. My original code was like 50 lines. That was time consuming. Harrison's code is like less than 10 lines, and it's just a snap and we're done with the illustration.
Any questions? I kind of have a question. So this is you're assuming that A1 and A2 are symmetric matrices.
Mm-hmm.
If they're not symmetric, it seems like maybe you might get lucky and get a convex set under some circumstances. But is anybody studied what happens if the matrices aren't symmetric, and does the image set like sort of measure, does the lack of convexity, if so, measure like how far away the matrix is from being symmetric?
That is a great question. I think the way I can answer I think I can answer it in positive. The reason is because if you have A1 and A2 that are not symmetric, and I can try to introduce new matrices that are symmetric. So essentially what happens is that this X transpose A1 of X, if it's not symmetric, what I can do is that I can decompose A in the following way. I decompose A as 1/2 A plus A transpose, and then plus 1/2 A minus A transpose. And then what happens is that this matrix is going to be symmetric, and this matrix is going to be anti-symmetric. Anti-symmetric means that if you take a transpose, it's going to be negative of it. And then because it's one is symmetric, one other is anti-symmetric, and therefore I end up with X transpose of a symmetric matrix. And then the other part, the X transpose anti-symmetric X times X is actually going to be 0. So if we have a matrix that's not symmetric, I can reduce it to a matrix that is actually symmetric. So as long as I am able to study symmetric matrices, I can answer the question for non-symmetric matrices as well.
Okay, thank you. Other questions? Okay, let's thank our speaker again.
Thank you all.
Thank you all very much. Stay tuned for the math club next week. I know it's like right before spring break, but what better way to kick your spring break off, right? Y'all have a good weekend. Thanks y'all for showing up, and thanks for everybody out in Etherland. And thanks again, Lance.
All right, bye y'all. Thanks.